Okay, now the moment you've all been waiting for, probably, right? When I say, all told, the monad is just a monoid in the category of endofunctors. What's the problem? Huh? And like we understand all the words, right? The monad, now we know what the monad is. A monoid, we've seen monoids, right? I mean, I started with monoids. Endofunctors, category, all these words are familiar. Category of endofunctors, right? I mean, yeah, of course we know what the category of functors is. Functors from category C to category D. The category of endofunctors is just functors from category C back to category C, right? So really the only tricky part there is the monoid part, because we haven't really explored the idea of monoid too much. The traditional definition of a monoid is in terms of sets, right? So a monoid is just a set of elements, like set of strings or set of numbers, right, with some kind of multiplication that is, well, like takes a pair x, y, right, and assigns it x times y or something like this, right? And there's a unit, right? But that's a set thing, right? And as I said several times, we don't like sets too much, right? And we don't like talking about sets. We don't like talking about elements, because that's the assembly language of mathematics. Right? We would like to get away from this and express the stuff in a higher language, right? And we sort of did with monoid by saying that, well, we can represent the monoid as just a single object category, right? And we have the single object, and then we have these morphisms, endomorphisms they are called, right? Because they go back to the same object. So every single object category is a monoid, and every monoid can be represented as a single object category. But really, we haven't really gotten away from sets still, because endomorphisms form a home set, right? Which is a set. So it's just another way of saying it's a set. So how can we get away from the set? Well, so I'll show you how this is done, how you can abstract stuff starting from this assembly language, and how you can get this higher level language. So we'll start with the set, but we'll try to recast whatever we are saying about sets in such terms that they are easily translated into categorical terms. So first of all, we have a set and we have multiplication, and multiplication is, well, I'll call it mu, okay? I'm going to use the same letters, mu and eta, okay? And you know why, right? Because eventually you want to get it in monoidal, in endofunctor category. So mu is, we take, it's a function from a set of pairs to A, right? So we have a set A, maybe I should call it N, oh, let's call it A, whatever, right? So we have a set A, we form this Cartesian product of A with itself, right? So that's our repository of pairs of elements, and for each pair of elements, we have a new element that's their product, the monoidal product, right? So like if this is a set of strings. You know, we have pairs of strings, and we concatenate them to get another string, right? And eta, well, okay, so we have this morphism, and we have this neutral element, the identity element, sometimes called E, right? That's an element of the set. And again, we don't like talking about elements. So we would rather replace it with a function, right? And we know that element of a set can be replaced by a function from singleton set, right? So I'll write the singleton set as you know, empty tuple to A. So instead of using identity element, I'll use this morphism eta. And multiplication will be this other morphism. I call it morphism, function. But functions can be generalized into morphisms, right? Okay. So some of these things can be generalized easily. For instance, this is a Cartesian product. Let's just drop the word Cartesian, right? And let's just say product, categorical product. So let's just write it as A cross A to A, right? And this, well, this is a singleton set. Well, we know it's a terminal object, right? So this is really a morphism from a terminal object to A. Okay, so this is more categorical now. And we can actually do this in any category that is a Cartesian category, right? Cartesian category is a category that has a product and a terminal object. Okay, so in a Cartesian category, we can pick one object, A, and we say mu is a morphism from A cross A, which is the square of the object, right? Categorical square of the object, to A, and we need another morphism from the terminal object to A. But that's still not a monoid, right? Monoid really sits in monoidal laws, which are two, associativity and the unit law. So how do we write associativity? Associativity is really, I mean, in terms of these guys, right? So we would multiply x and y, right? So mu acting on a pair xy, and then multiply it by z, right? We would like this to be equal mu acting on the pair x and the multiplication of y and z. Right? So that's associativity written in terms of mu. We haven't done much, right? But okay, that's a good starting point. Now unit laws. Unit laws would be like when you multiply a unit. So a unit, you can get a unit by mapping the terminal object or the singleton set, right? Well, just acting with eta on the singleton object, on the element of the singleton set. Eta acting on the element gives you the unit element. So that's the unit element. Eta acting on a singleton element gives the unit element in A. And this multiplied by some x should give you back x, right? And this is left unit, and there's also right unit, eta acting on equals x, right? So this is slightly more general because it uses morphisms mu and eta, but still, I mean, this is still using elements, okay? So it would be nice if we could rewrite this in a point-free way, right? So like if you could say, so this is like these functions acting on a triple x, y, and z. So like a triple x, y, z, and it's acted with some combination of functions, right? So it's sort of like we get an element from A cross A cross A, right? And we just say, let's combine these two here, right? And so x comes from here, y comes from here, and z comes from here, right? And now we are applying mu to this. But a product, right? Remember, product is a bifunctor. So we can apply two functions at once, right? So we are acting here on a product. So let's, like look at this as one element of the product and this is another element of the product. We are acting with mu on this, and we are acting with identity on this. So we are using two functors, two morphisms, right, as a pair, or in more general as a product. Product of two morphisms acting on a product of two objects, right? So mu acting on A cross A will produce A, and identity acting on A will produce A. Okay? Now this we can act with just mu on this, right? And we'll get A. And now we would like to do a similar thing, but starting with A cross A cross A. Right? This is also A cubed, right? It's a triple, but in a slightly different pairing. And we can act on this using ID cross mu. And we go to A cross A. And then mu will give us A. Right? So, I'm just like using the language of pairs, or the language, this is in the language of pairs, this is in the language of product, this is like whole set thing, and morphisms. Because I want to do it in a point-free way, right? So I want to combine morphisms into products of morphisms, like this, acting on products. Product of morphism acting on product. Right? I can do that. Well, the only problem is that these two things are not equal. I mean, I would like to say something like A cross A cross A, right? A triple, a tuple, right? But it's not really equal. So it just so happens that this is remember, product was sort of like a monoid, but up to an isomorphism, right? Remember? So product is just product in the category itself, right? So we have two things. We have a product in the category, and we have mu, which is our product in the monoid. They're completely different. Mu is just a morphism, whereas product here is a product in the category. And this product in the category is sort of like a monoidal product, but it's only up to isomorphism. So let's say there is this isomorphism, let's call it alpha, called associator, okay? That converts this pair into this pair, right? I mean, in Haskell we would define it as alpha acting on, well, we would just like pattern match it. Right? Alpha is a function that takes this type and produces something of this type. It just rearranges them. Right? The signature of alpha is a, well, actually it can be this. Yeah. No. Well, let's just do this. No, let's just do this. Right? This could be different types. Don't have to be the same types. Now here we have the same type because that's our construction, because this is what we need for mu. But in general, this is true right? And we also know that that there is a unit, the unit type, right, is a unit of pairing, right? So if we have a pair of unit type and A, we can transform it into just A, and that we'll call this lambda. Lambda, and we pattern match it. You know, here we can pattern match with anything. This is X, it just gives us X. And this is invertible. These are isomorphisms. You know, the inverse of this is the same. It's just take X and produce, right? Lambda inverse equal acting on X is equal unit value with X. And that's the inverse of this, right? So what? So this just shows you that taking a pair, the pair type, the product in Haskell, right, is monoidal, but up to isomorphism. And there are these three isomorphisms: alpha, lambda, and there's another row, which is a right unit, right? So it takes a unit, and maps it into A. So that's what I was saying, that unit is the unit of product, and product itself is associative, but it's only modulo isomorphism. So in general, you know, if we have a category in which we have this kind of alpha, lambda, and rho, and these laws that say, you know, that there is alpha isomorphism between A cross A cross A cross A cross A, and there is an isomorphism between we call it the monoidal category. So a monoidal category is just a straightforward generalization of this. It's a category in which we have categorical product, right, and terminal object. Well, actually, we can do better than that. We can say, why do we have to talk about product? Remember, we also had coproduct. Coproduct had the same property. With coproduct, with either, right? It was also a monoidal thing, right? It was associative up to isomorphism, and it had a unit, which was the void, right? An empty set. Okay. So that's also monoidal. So in general, we can have a monoidal category, and the only requirement for a monoidal category is that it has a product, and this product, what can we say about this product? We only say about this product that it's a bifunctor, right? It takes one object, another object, and produces a third object, right? So it takes a, right. So it takes A, B, and produces A cross B. Now this could be a product, this could be a coproduct, but in general we call it a tensor product. If we have a monoidal category, so first of all, we need a monoidal category. So it's a category which has a tensor product and it has the identity object. Okay? So identity object for categorical product was the terminal object. Identity object for either or for coproduct was the initial object or void. Right? So in general, if you have a monoidal category, there will be an object called identity object called I. So a monoidal category has a bifunctor like this and has an object I, which is called a unit object. Right? So now, if we have a monoidal category, we can have a more general definition of a monoid. Right? We can define a monoid as an object in a monoidal category. Let's call this object M. Right? With two morphisms. So we have an object M, we have morphism mu that goes now from M cross M. See how I'm generalizing things a little bit at a time? I started with a pair, then I went to a product, now I went to a tensor product. And every time I generalize a little bit, I go from set, I went from set category, then I went to a Cartesian category, and now I'm saying monoidal category. Every time I'm upping the level of abstraction a little bit and replacing pair with Cartesian product with product, and now I'm replacing with a tensor product. More general. Right, let me parentheses. So just goes from M cross M, tensor product, to M. And eta, which used to go from a terminal object, now goes from I to M. So this one sort of generalizes this idea of picking a unit element in M. Right? This is how you can think of this. Except that I now can be much more general. Could be in a Cartesian category, this will be the terminal object. In a bi-Cartesian category, it will be an initial object if we use coproduct, and so on. Now, in general, you know, there are two kinds of these monoidal categories, strict and lax. What I described here, because we started with a product in set, I had to do a lax category because pairs are not associative, strictly associative, right? I had to introduce this associator alpha here, and this left unitor and right unitor, because unit was not really strictly unit, it was up to an isomorphism. So I had these three isomorphisms on top of everything, right? So a Cartesian category, a monoidal category can be lax, and when it's lax, then the laws of identity and associativity are up to special isomorphisms. Now these isomorphisms, alpha and lambda, now will be natural isomorphisms. Okay, because product is a bifunctor now. Right? Product is a bifunctor, so I will have to use mappings between functors. So I'm saying, A cross B cross C. That's a functor in A, B, C. Right? If I want to say this is the same as A cross B cross C, parenthesized differently, then I'm mapping one functor into another functor. And mapping of functors is a natural transformation. So this will be natural isomorphisms. But there are also strict monoidal categories. A strict monoidal category has equalities instead. Right? So associativity is just equality of A cross B cross C is just equal to A cross B cross C. And the same with unit. Okay? So there are these strict monoidal categories. So now, for the final thing, let's pick a category of endofunctors. Okay, so a category of endofunctors, these are endofunctors are from C to C, right? C is a category. Endofunctors, there's are functors from C to C. They form a category, right? In this category, morphisms are natural transformations between these endofunctors. Now, what is the tensor product that we can come up with in this category of endofunctors? There's one very natural tensor product, namely tensor composition of endofunctors. Any two endofunctors can be composed, right? So if we have a functor f, endofunctor f, we can compose it with endofunctor g. So this circle here, why don't we treat this as a tensor product? It is a bifunctor in the category of endofunctors, meaning that if you apply natural transformations to f and g, right, you can lift them. It's associative, right? F, G, H is actually strictly equal F, G, H, right? No associator necessary, it's strictly equal. And what's the unit here? Identity functor, right? Identity functor. Identity functor with some f is the same as f, and it's the same with f after identity functor, right? So hey, we have a very, very simple monoidal category here. With identity, with multiplication, tensor product, right? Which is just, I mean, it's a kind of funny way of looking at it, right? That composition of two functors can be treated as a tensor product of these two functors. But it is. So now, okay, so now we have a monoidal category. Monoidal category of endofunctors, right? We can pick an object there. What it means is picking an endofunctor, right? So we have this CCC, this is this category where we have endofunctors, right? And it's monoidal. Now we can pick one object here, which is one particular endofunctor, and we can say, okay, if we can define a morphism in the category of endofunctors from, so we have this ID here, right? So, and this is our T. Let's call it T, okay? This one endofunctor that we picked. So we have a morphism from ID to T, right? In order to form a monoid, we have to define this eta, right? Which is a morphism from the unit object to our monoidal object. But now these objects here are endofunctors. So a morphism between endofunctors is a natural transformation. So eta here is a natural transformation from ID to T, right? That was our return, right? And now multiplication, mu, goes from T squared to T, right? That's our mu. T squared means T after T. Square in the sense of the tensor product in our category. A tensor product in our category is just composition of functors. So it's T composed with T, right? And it must be a morphism in this category. So it is a morphism in the category of endofunctors. It's a natural transformation. So a monoid in the category of endofunctors is a monad, right? That's it. Okay? Thank you.